All right, let's go ahead and talk about one last concept for our quarter. As we wrap up chapter 11, we wrap up the third quarter material. As we wrap up this in-depth study of all things lines, all things polygons, I want to talk about this idea of distance again. And of course, we know for distance, if you're measuring distance between 2 points, class, that's simply a straight line, right? The distance between 2 points is a straight line. So we said we could define the distance between 2 points taking the change in x squared and the change in y squared, correct? But there's 3 ways we define distance, right? Going back to geometry last year, we can define distance as the distance between 2 points, which is a straight line. We could also define the distance from a point to a line. How do we define the distance from a point to a line?
The line drawing perpendicular.
The perpendicular, correct? So that's what we're going to focus on today. We've got, one of the first things we talked about was how to find the distance between 2 points. What about the distance from a point to a line? And since we've done a lot of work with perpendiculars lately, I feel now's a good time to go and cover that. We've got the foundation that we need. So, next thing in your notes, finding the distance from a point to a line. There is a third definition of distance we'll get to at the end of the hour. If not, we'll get to it tomorrow. But we'll stop here for now and emphasize this. Distance between a point to a line, first of all, make sure you know it's the perpendicular. And then let's do an example problem together. Let's find the distance from the point 11, 2 to the line 2x plus y equals 4. The distance from 11, 2 to the line 2x plus y equals 4. So, quick sketch, right? There's a point, there's a line. I'm going to say this point is 11, 2, and I'm going to say this line is 2x plus y equals 4. Probably looks nothing like that, but it doesn't matter because we don't trust our eyes anyway, right? So geometry has really freed us from the hassle of trying to draw things correctly. Isn't it wonderful? Picasso probably took geometry and loved it so much he started drawing things really weird. So, well, you can trust your eyes anyway. 2 eyes on the same side of one face, perfectly normal. Yeah, if you're a flounder. Anyway, so we wanted to find the distance. So we said it's going to be the perpendicular. So what I want to know is how long is that, correct? Well, step number 1, you've got to know the equation of this perpendicular. So step number 1, find the equation of the perpendicular. And this is pretty straightforward because we've done this a lot the last couple of lessons. If the line to which the perpendicular is drawn is 2x plus y equals 4, then any perpendicular has to start how, class? X minus 2y equals something. This particular perpendicular comes from point 11, 2. So therefore, this particular perpendicular is x minus 2y equals 7. Really easy first step, correct? You're given the equation of a line, and you're given a point, and you're asked to find the distance from the point to the line. Get the equation of the perpendicular. That's not hard. Step number 2, we want to know what is this point. We know from a point, one and only one perpendicular may be drawn. That's why we said the perpendicular. And we also know that 2 straight lines can intersect at but one point. What is that point? So step number 2, find what we call the foot of the perpendicular. Find the foot of the perpendicular. Find that point. Well, all that is a point of intersection, right? Between 2 lines. How do we find points of intersection between 2 lines?
Addition.
A system of equations, which we could solve by either addition or substitution. So in parentheses, put system as a reminder to yourself. That's how you're going to find that foot of the perpendicular. You're going to set up a system of equations. You're going to say x minus 2y equals 7 and 2x plus y equals 4. And do we want to do addition or substitution, Jamie?
We can do addition.
All right, and so if we're going to do the addition method, which variable you want to knock out?
The y.
The y already has different signs. And by the way, the y will always have different signs because it's a perpendicular, right? So you can at least bank on that much. Multiply the bottom equation by 2, so that my bottom equation becomes
4x plus 2y equals 8.
Alright, we'll scribble this out here. That allows, as I add the equations, the y's to cancel. What do I get when I add the rest of it here, Quentin?
5x equals 25.
7 plus 8.
15.
15. And so therefore x is equal to 3. Well, that's the abscissa of the foot of the perpendicular. We still need to get the ordinate, so of course, Quentin, we're going to
Plug in the 3.
Into
Equation.
one of the two original equations here. So let's just plug it in right here, for instance. And if I plug in the 3 here, what is my y value going to be?
Negative 2.
-2. All right. Any questions on the first two steps? Step 3, it gets even easier. Because I now know a point and another point. And I want to know the distance between them. Oh, you mean find the distance between 2 points using the distance formula? Yeah. So find distance. Use the distance formula. So what is the change in x, class?
8.
Squared?
64.
What's the change in y?
4.
Squared?
16.
16 and 64 adds up to?
80.
80. I feel like I can reduce that. How could I factor the 80?
16 and 5.
16 and 5. And so my final answer for the distance from this point to this line is?
4 units.
And there we go. There's our answer. Seem pretty easy? Find the equation of the perpendicular, find the foot of the perpendicular, so we can go back to what we know with distance. Is kind of where it all comes back to. We know how to find distance between 2 points, and that came out garbled. And so make it that way. Make it so you can find the distance between 2 points. Find the foot of the perpendicular by first finding the equation of the perpendicular, and then get the distance. All right, so then, let's suppose, change it up now. I want to find the distance from the point 1, 4 to the line 2x minus 3y equals 3. Woo, woo, dropping things. All right, from the point 1, 4 to the line 2x minus 3y equals 3. You don't have to draw a picture. I like to. I'm a visual kind of person. I like to see what's going on. So I'm going to draw a point. I'm going to say that it's 1, 4, whether it is or isn't. It really can't be because it's not on the Cartesian plane. I'm going to draw a line. Draw it goofy like this time. I'm going to say that this line is 2x minus 3y equals 3, even though it probably looks nothing like 2x minus 3y equals 3. And then I'm going to say that my perpendicular is like that. What do I do first? Quentin.
You get the formula of the perpendicular.
Not the formula of the perpendicular, but the equation of the perpendicular. And I know the equation of the perpendicular, class, has to start how?
3x plus 2y.
Yeah, 3x plus 2y equals something. Jamie, what's the something?
11.
11. So I now know that this, which granted, the perpendicular technically goes infinitely, right? It's the whole thing, right? But anyway, 3x plus 2y equals 11. That's my perpendicular. Once I know the equation of this perpendicular, what do I need to find, Jamie?
You need to find the foot.
The foot of the perpendicular. Basically, where does the perpendicular intersect my line? And to find that point of intersection, class, we're going to use a system of equations. So we set up our system. We say that 2x minus 3y equals 3 is going to intersect 3x plus 2y equals 11 somewhere. Quentin, your choice, sort of.
Get rid of the y.
There's really not much. You can't really use the substitution method effectively here, and the y's are a clear choice. Multiply the top by
2.
bottom by
3.
Top equation becomes what, Quentin?
4x minus 6y equals 6.
Bottom equation, Jamie?
9x plus 6y equals 22.
Distributing a 3 here.
Oh, 33.
33. And we add these together to get Jamie.
13x equals 39.
So x equals
3.
And once I know that the x is 3, Quentin.
Plug it back into the bottom equation.
Yeah, I like to avoid negatives. I'm going to go here. Of course, 3 times 3, class. Move it over as a, to get 2y equals
2.
So y equals 1. So that means the foot of the perpendicular, Jamie, is
3, 1.
3, 1. And once I know that point, what do I do next? Quentin? Remember, my goal is to find how far this point is from this line.
Yeah, find the distance.
Yeah, find the distance between the 2 points, because that is the distance to the line. And to find the distance, remember, we're going to take change in x squared, class,
4,
and change in y squared.
9,
And so apparently the distance is the square root of 13 units. Questions on that? Seem pretty easy. All right, at your seats, I want you to read page 226, number 1b. Page 226, this is a 1b. That's not a 16, that's a b. As in beta. Already starting to dry up out there. That's real good.
I was going to ask what we were going to do for PE, but I knew you would just say we'll find out.
Oh, yeah. Well, we will. I mean, if it decides to resume raining, which they're saying it shouldn't at this point, then we'll make other plans. But sit-up competition sounds like a good idea, doesn't it, Quentin? Yeah. There's the push-up competition where the guys try to earn the man card. Sadly, fewer and fewer each year are able to do it. They didn't give you a particularly nice equation to work with, did they?
Oh, it worked out okay though.
Did we get 6x plus 7y equals 9 for our perpendicular? All right. Did you find the foot of the perpendicular to be negative 2, 3? All right. So did you get the distance to the square root of 85 units?
I was messing up at the start, but I was on the right track.
On the right track at this point? Any questions at all on this? All right. Do D. Letter D now. So it'll be that looks much easier. It's like the reward for surviving letter B. Quentin's already got it. Show off. All right. Quentin's like, you are correct. Good job, Mr. Ndasky. All right, Jamie got it also. Excellent. Let's take a look at number 2. Go ahead and read the instructions for number 2. And we're going to do letter B together, but read the instructions for number 2 for us, Jamie.
For triangle ABC, find the length of one altitude and the area of the triangle.
You said find the length of the altitude?
Of one altitude.
One altitude.
In the area of the triangle.
Area of the triangle. Ooh, okay. All right. So they give us 3 points, right? So on your paper, draw a nice big triangle with room to write inside. And it's triangle ABC, of course, because we're boring that way. -4, 8. 2, -2. And 6, -3. The length of an altitude, just one altitude, and the area. Well, how do I find area of a triangle? Well, earlier this year we talked about ways to find the area if we knew all 3 sides, Heron's formula, if we knew 2 sides and an included angle, or if we knew other angles we could put it all together. Do I really want to find the length of 1 side, 2 side, 3 side, and use Heron's formula? Probably not, because probably I'll get radicals. And remember Heron's formula? Square root of half the perimeter. How are you going to do half the perimeter? We got all these radicals, right? We're not using Heron's formula. In fact, even to use two sides and an angle, that's still radical times radical, presumably. And then you got to use two angles of inclination. There must be an easier way. Well, how do we do it in geometry? I mean, this is analytic geometry. We're harking back to a lot of geometry concepts. How do we find area of a triangle? T equals a half BH. Well, any side could be considered the base. But whatever side we call the base, we would need the altitude to that side. Does that make sense? So, begs the question, which side do we want to be the base? Don't screw this up, Quentin.
AB.
All right, we're just going to go AB as the base. All right, if this is the base, then we need the altitude as well. We specifically need the length of the base and the length of the altitude, right? Well, the length of the base shouldn't be too bad. Just use the distance formula. And what do we get? I'm going to leave it unreduced here. Okay, I'm going to leave the square root of 136 units. So there's the base. Now for the altitude. There's just one problem. I can't find the length of the altitude right now. Why not?
Because you don't have a
You don't know the midpoint?
I don't know what the, is this the midpoint?
No, it's the...
Not necessarily the midpoint. Oh. How do I find that point? Where the altitude and the base intersect.
Perpendicular, so...
In order to find a point of intersection, I've got to use a system of equations. I don't know either equation, but there's only one equation I can get right now. What's that?
the base.
The equation of the base, right? So let's go ahead and get the equation of the base here. And Quentin, to get the equation of the base, you said it a moment ago, it starts by knowing the slope. So what is the slope of our base, anyone? Good, 10 over negative 6 or negative 5/3. All right, now, if that's the slope, I know how my equation has to start.
Y equals...
Remember, slope is negative a over b. So I know what a is, I know what b is.
5x.
Yeah, 5x minus 3y.
Plus 3y. The negative is already accounted for. Remember, we changed the sign on the slope. So since we have a negative, it means the equation must have a positive. Apparently, the equation of the base starts 5x plus 3y equals something. Now, how do I finish that equation? Plug in either a or b, one of the 2 points that we know is in that line segment. Let's go with b. I think that'd be easier. 4. And that's not too bad. So we have the equation of the base, but we also need the equation of the altitude. Well, I know how the equation of the altitude is going to start.
3x minus 5y.
Equals something. How do I figure out the something?
Plug in C.
Good. Not A or B, because neither of these is a point in the altitude. The only point I know for sure is in the altitude is the top vertex, C, 6, negative 3. 33. And if I make a system of equations, I can find this point, this foot of the perpendicular. Well, let's multiply the top by
30.
I go
Sorry,
5 and bottom by 3, so my top equation becomes what, Quentin?
25x plus 15y plus 1.
And the bottom equation, Jamie?
By 3, and it'll be 9x minus 15y equals 99.
Alright, we cancel the y's, and I'm starting to get a little nervous here. What am I getting for my equation now, anyone?
34x equals...
119.
Oh. So you're... Does that reduce maybe? Try putting 119/34 into your calculator and see if it reduces.
I have 3.5 and I did.
Oh, you did it as division. I wanted a fraction.
3.5.
3.5. Oh, okay, or 3.5 or 7 halves was what I was kind of looking for there. Okay, that's not as bad as I feared, I'll be honest. At first I'm like, 34 doesn't divide evenly. And I'm like, wait, there might be, you ready for this? A 17 in both of them. How the math brain works. I'm like, maybe, I'm hoping, because if not, that's a really ugly x value. Okay, that's actually not that bad, all right? Now let's plug that in. That's not bad to plug in, especially with the calculator's help, into the top where there's no negatives, right? So 7 halves times the 5, then move it over as a negative that. I'm just going to say negative 35 halves. So add whatever you have on the calculator, but as a negative to the 4, then divide by 3. And give me a second. What do we get?
Negative 9 halves.
Negative 9 halves. Okay, that's not too bad either. Or negative 4.5. Okay, so I know that point. Now, why exactly did I want to know that point? Ultimately, what are we finding? It feels like geometry again. Okay, we're working through this proof. What are we trying to do again, class? Find the? Nope. Ultimately, area. We want the area. To know the area, we needed a half base times height. We found the length of the base. I needed the length of the height. But to get the length of the height, I needed both points. Well, now that I have both points, let's go ahead and find the length. But remember, since we got the fraction here, it might behoove us to rethink my 6 as a 12 tooths and the negative 3 as negative 6 halves. Jamie's like, I am not saying negative 6 tooths. I've got my pride. All right, so what is the change in x? 5 halves squared.
25.
And the change in y?
3 halves.
3 halves squared.
9 halves. Or 9/4.
9 fourths. 25 fourths plus 9 fourths is
34 fourths.
square root of 34 fourths. All right, now hold on here. Square root of 34 fourths, but I can take the square root of the 4.
Square root of 34.
Let's do square root of 34 over 2. Now realize this is the square root of 136 over 1. So my denominators actually multiply great. 2 times 1 times 2, 4. And then the square root of 136 times the square root of 34 is going to give me the square root of what? What is 34 times 136? Really big number. Somewhere in the thousands. 34 times 136.
Need square root? Or?
No, I don't want the square roots yet. Which is 136 times 34. 4624. All right, so that means the square root of 136 times the square root of 34 gives me the square root of 4,624. Does that come out evenly?
Yeah.
All right, that's awesome. So the square root of that number is 68. So I'm getting 68 over a 4, which that actually, that divides evenly to get
17.
So that's the area, 17 square units. If you were to plot those 3 points on the Cartesian plane, connect them, shade them in, you'd be filling in exactly 17 square units. Probably at such weird angles you wouldn't actually be able to count the boxes you were filling, admittedly, but it would add up to exactly 17 square units. Questions on this? By the way, it would have worked the same, and for sake of time we won't show it, no matter which side he had picked as his base. Now he would have had a different length for his base, and the altitude would have also had a different length, but it would have worked out to 17 square units, regardless of what he picked. Questions on this? Might have been easier if he picked a different side, might have been harder. We'll never know, because we're not going to do it because we're lazy. Let's take a look at number 3, and read that for us if you would, Quentin. What are we doing here?
Show that each pair of lines is tangent to a circle with the given point as center.
So each pair of lines is tangent to a circle. Okay, so this is fun. So I've got some random circle. We don't even know what it is, right? But I've also got a couple lines. So I've got a line like this. I got another line like that. And it says show that these lines are both tangent to a circle with its center at 0, 0. So tangent, remember, means the line crosses or touches one time, right? So we got something like this. Does that make sense? We got 2 lines, and if we drew a particular circle, these 2 lines would both be tangent to it, assuming the center's at the origin. Does that make sense? So the two lines they give me, Quentin, in 3a are
3x plus y equals 10 and x plus 3y equals 6.
3x plus y equals 10, and you said,
X plus 3y equals 6.
ooh, are these two lines perpendicular to each other? No. Reciprocal slopes, but not negative reciprocal slopes. Okay, so whatever. Show that they're both tangent to the same circle, centered at 0, 0. What does it take for lines to be tangent to the same circle?
Perpendicular to radius.
Oh, that's true. They will be perpendicular to the radius. So, I mean, you know, we got a radius here. It's going to be perpendicular to that. We got a radius here. It's going to be perpendicular to that. What does it take for a line to be tangent to the circle? For instance, this line is perpendicular to a radius, right? I just have to extend the radius a little bit, right? It's perpendicular to it.
At one point.
Yeah, it has to touch the circle at one point and be perpendicular to the radius. So let's put those two thoughts together.
They have to have at least 1 point. Where they going?
Why did that line that was perpendicular to the radius not be tangent to the circle? Why didn't it touch at one point? Thinking in terms of distance.
Because one point in the circle shares that point in the line.
How far away from the center was this line? Further away than the radius was. Ah, so for lines to be tangent to a circle, their
The same distance as the radius.
distance from the center must equal the radius. Now, they don't tell me what the circle is. They just say there is a circle. So for these lines to both be tangent to the same unknown circle, they must have the same distance from 0, 0. If these two lines have the same distance from 0, 0, then there is a particular circle that if I open the compass up that exact distance, I could draw a circle that would be tangent to both of them. Remember, we actually did this construction. I gave you two lines and I said, draw the circle or construct the circle that was tangent to these two. So what you did was you found, how do we draw this again? We found equidistant from this line and that line. I'm trying to remember how we did the construction. It's been a while since we did the geometry.
It was the angle bisector of the
Yeah, that's what we was. We extended them to form an angle bisector. And we picked a random point. We constructed another perpendicular. And that gave us the radius. So we actually did the construction. When we're doing this, sans construction, no construction necessary. We just need to show that these two tangent lines are the same distance from the origin. So, at your seats, find the distance from 0, 0 to 3x plus y equals 10. right, so first thing I did, working with this line that we say is going to be tangent to this unknown circle, is, well, what is the equation of the radius? Well, x minus 3y equals something. Plug in 0, 0, and we get x minus 3y equals 0. So that's the equation of the radius. We used to say the equation of the perpendicular. Same thing. Then we'd say, okay, let's find the foot of the perpendicular, or the point of tangency. System of equations. I found it to be 3, 1. That's the point of tangency, or the foot of the perpendicular. Then find the distance, or I say length of the radius. And it comes to the square root of 10 units. So far so good? We gotta do the same thing here. What's the equation of this radius going to start out as, class? 3x minus y equals, and the only point I can plug in, so it's also going to be a 3x minus y equals 0. So I'm going to have to take the 3x minus y equals 0 and the x plus 3y equals 6, make a system to find the point of tangency. Multiply the top by 3 to get 9x minus 3y equals 0. Cancel. This one's not as pretty. What do I get? 10x equals 6, so x is 3/5. Oh. Well, plug in the 3/5, subtract it over, divide by 3. What do we get for the y value? And 9/5? Okay. Trying to do it in my head, I wasn't sure if I had it right. So we know that this point here is the point 3/5, 9/5. Now we need the length of the radius. Well, what is the change in x squared? 9/25. And what's the change in y? 9/5 squared. 81/25 gives me the square root of 90/25. Something's not right here. Because that gives me 3 times the square root of 10 all over 5. Show that each pair of lines is tangent. Whoa, am I misreading something? I thought somebody said the origin was the center. Oh, 5-3 is the center. Okay, so if you've been screaming at the screen the whole time on YouTube, 0, 0 is not supposed to be my point. 5-3 is supposed to be my point. That really messes things up, doesn't it? Well, with nothing else, we did establish 0, 0 is not the center. How come y'all didn't catch that? You're just going along with it. Oh, man. But definitely not the same distance. So they're not tangent to a circle center. I don't know where I got origin from. Does it mention origin anywhere? It just says given point as center. My brain says origin is the center. I don't know what I got. Wow, 5-3 was supposed to be the center. Okay, all right. You know I can't just let this lie. Well, actually, let me hold that thought. We said we had a 3x plus y equals something. Obviously, that changes the somethings, doesn't it? For the white one, if 5-3 is the center, correct? Then we plug in a 5 and a 3, and we get -4. All right, and so putting a -4 here, that gives me a 10x equals 26. That's hideous. And so now x doesn't work out nearly as nice. 13/5. There's that side of me that wonders if I'm still doing something wrong. 5-3. 5-3. 5-3. It's -4. Plug that in with the 3x plus y equals 10. Multiply the 3. It is 9x plus 3y equals 30. You do cancel. You do get the 13/5. That's awful. All right, let's get the y value right here. 13/5 times 3. Make it a negative and add it to the 10. It's like 11/5.
I got 11/5.
11/5. Oh, man. And so now we got to find the distance from 5-3 to 13/5, 11/5. This is awful. Make this a 25/5, make this a 15/5. What's the change in x? 12 fifths squared. Change here? 4 fifths squared. That's going to be 144 plus 16 more 25ths. That's square root of 160 25ths, which is 4 times the square root of 10 fifths units. That's the radius. Now for the yellow guy. Stupid. All right. Well, again, 5, 3 is my point. 5, 3 for my perpendicular gives me what ending for my equation of this radius? 18. So this then has an 18 initially. Not 3x plus y, 3x minus y. So there's a second mistake. It's supposed to be a minus y. So I already had another issue in the last equation anyway. Because the perpendicular is 3x minus y equals.
It's 12.
So it's going to be a 12 then. See, I want to work these things out ahead of time. Like, I game planned how I was going to do it, but I never game planned, like, I never actually figured the answer ahead of time. So that's what I get. Note to self, if you don't work it out ahead of time, you don't know. So then we multiply a 3, which gives us a 36. And that gives us a 10x equals 42, which gives me still an ugly answer for x. 21 fifths?
Yeah, 21 fifths.
All right, so my x value is a 21 fifths. Plug that in here. Subtract 21 fifths from 6 and divide by 3. Subtract 21 fifths from 6, divide by 3.
3 fifths.
3 fifths? That's not too bad. Okay. Again, let's think of 25 fifths, 15 fifths here. What's the change in x?
4 fifths.
4 fifths squared is 16 25ths. Change in y?
12 fifths.
144 25ths. You see where this is going? Sure enough, we get the square root of the 160 25ths. We get the 4 squared of 10 fifths. Yes, these are both tangent to that circle. They have an awful looking radius length, but they're there, okay? Now, if we want to go a step further, we should stop. No, we don't stop. It's not what we do.
Let's stop while we're ahead.
Yeah.
Stop while we're ahead. No, because we got another, while we're on this note, right? In geometry, we said if we draw 2 tangents to the same circle, what's going to be true about those 2 tangents?
Perpendicular. No. Intersect them.
You draw 2, well, it's true. They will intersect just once. But from that point of intersection to the points of tangency, they're going to be equal to each other. Well, these 2 equations are not perpendicular, right? They're just going to intersect. Where will they intersect now? Set up a system at your seats. Let's find where those 2 lines intersect, because somewhere out here in space is going to be a point of intersection. I want to know where it is. I hope it works out well. Oh, it does. It does. Yes. You got it? That's not bad at all. I like that. I really like that. 3-1. Now, these points of tangency are in terms of fifths, though. So I want to think 15 fifths, 5 fifths. What's the distance to the point of tangency? Change in x? 6 fifths squared.
36 fifths.
Change in y?
2 fifths.
2 fifths squared.
4 fifths.
I'm getting the square root of 40 fifths, or the square root of 8, or 2 squared of 2 units. That's how long this tangent is. Let's go here. Change in x? 2 fifths squared is 4 fifths. Change in y? 6 fifths squared is 36 fifths. It's also going to be the exact same. So showing that yes, once you actually get the right circle centered at 5, 3, not this ambiguous 0, 0 I made up, then yeah, they are equal tangents. And they're actually tangent to the same circle. And yeah, anyway. Number 4. Number 4. There's a third way we define distance. And I was supposed to get to this about 5 minutes ago, but we got hung up on something. Somebody's fault.
No.
Let's blame Ethan. He's not here.
Yeah.
All right. Now that I erase all of this. Oh, poor YouTube people. Hopefully they could follow what was going on. Oh my. All right. Did y'all follow somewhat what was going on? By the time it was done, at least? All right. 4a. The distance between parallel lines. How do we define the distance between parallel lines, class? The length of any perpendicular that goes between them, right? I've got one parallel line, I've got another parallel line, but any perpendicular between, that's the distance, correct? Well, they give me a couple parallel lines on 4a. One of them is 5x plus 6y equals 25, and another is 5x plus 6y equals 72. Even if they hadn't told us these were parallel, we know, correct? Now here's the thing. I can find the distance from a point to a line if I just find the perpendicular. But that means I'm starting with a point. I don't have any points. So let's come up with one. Let's come up with a point that works. The easiest way to do this? Assume that one of the values is a 0. Let's make the hard one 0. The 0 for my y. Because let's face it, 25 doesn't divide by 6 well anyway. Bam! Y is gone. What's x? Do you see that 5, 0 must be a point in this line? Now you only want to do that with 1, because you could say, oh, I see what we do, put a 0 here and 0, 12. Well, yes, 0, 12 is a point in the line, but it's not necessarily at the other end of that perpendicular. Does that make sense? So we just get a point in one of the lines. Now then, ignore this line. I have point, I have line. Let's find distance. Start by finding, class, the equation of the perpendicular. How does the perpendicular's equation start?
6x minus 5y.
And if I take the point 5, 0, notice there's a second benefit to that 0. Yeah. What do I get? 30. Love zeros. Next thing I need to do is I need to find the foot of the perpendicular. Yep, multiply by 5, multiply by 6. Is this as bad as it looks? I think, did I mess this up?
I hope not.
I don't think I did.
Or I hope so.
I get a 61x equals 540.
Yeah.
So that means x is 540 61st. Does that reduce? It can't. 61 is prime. Okay, here's what we're going to do. This might be right or it might be wrong. Here's how you check. Go to both of the equations, plug it in with the calculator. If you get the same y both times, it really is correct. If you get different y's, we screwed something up. So, plug the 540 61st in here. Times 5, make it a negative, add it to the 72. Then divide by 6.
282 over 61. That's what I got.
You said what?
282 over 61.
All right, she says that's what y equaled in the top. Confirming or denying? Okay, all right, now plug it in here. So the 540 61st times the 6. Let's double switch. Once you've got that, subtract 30 and divide by 5. So 540 61st times 6 minus 30, divide by 5. Do you get 282 61st again? That means that the foot of the perpendicular is 540 61st, 282 61st. There had to be a better point than 5, 0. Stay with me though. Now we get to find the actual distance between the parallels. What is the change in x? Never mind, but you would do that. Change in x squared. I know the change in y squared. It's 282 61st, and it's just going to be an awful answer. But that's how we would find the distance between parallel lines. Good news is, on the exam, you're not going to have to find the distance between parallels. Point and line, yes. 2 points, yes. It gets pretty gnarly there. All right, homework, page 226. Just 2 of these, and 2 of the easy ones, not the hard ones. Page 226, number 1C and number 2A. Number 1C and number 2A. Boy, that was a fun lesson. Anytime I have start to sweat during the lesson, you know it had to be a good lesson. Lesson 133 is your exam. That's Monday for you if you're watching on YouTube. Lesson 133. Oh boy. All right, note to self. 4A works out awful. Maybe I should have tried 4B. Those equations look a little easier. No. They're on page 226. What do you think, Quentin? 4B, should have gone with that?
They look easier.
5s and 6s are nasty. 2s and 3s have got to be easier, right? Anyway.
But there's a negative in that.
I'm just ready to run away.
Yeah, I don't know. Anyway, have a wonderful rest of your day, and you are dismissed.